Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at converting recurring decimals to fractions. So remember, recurring decimals are ones like this. This is written in exact form. The digits after the decimal place go on forever. So 0.8 recurring is 0.88888. The 8s go on forever. So we learned previously how to convert terminating decimals to fractions. If we had something like 0.35, we just wrote the digits without the decimal point on top and the lowest power of 10 on the bottom, because 5 is in the hundredths column, and then we simplified. That's how you go from terminating decimals to fractions. I just wanted to show you why that won't work with recurring decimal places. The point is, we knew to put 100 on the bottom because 5 was in the hundredths column. It was the lowest place value 10, the last digit after the decimal point. Unfortunately, for something like 0.8 recurring, there is no last digit after the decimal place. So we don't know what power of 10 we can put on the bottom. This method for terminating decimals isn't going to work for recurring decimals. But fortunately, there is a quick method. So you use this quick method if the decimal only has a recurring part. That means that all of the digits after the decimal place are repeated. So for the numerator, you write the reptend. What is the reptend? It is just all of the digits that are repeated. So here, with 0.8 recurring, 8 is the only digit repeated. So what we're going to do is just put an 8 on top. So denominator or bottom number is a string of 9s. It's all 9s. How many 9s do you put on the bottom for the denominator? Well, the number of 9s is the number of digits that are repeated. In this example, there's only one digit that's repeated, so I put 1 9 on the bottom. 0.8 recurring is 8 over 9. Now, sometimes you will need to simplify, sometimes you won't. I can't simplify 8 over 9. They have no common factors, so I leave it like that. Let's look at 0.27 recurring. So this only has a recurring part because all of the digits, the 2 and the 7 here, they repeat infinitely many times. So I'm going to use the quick method. So what I do is I put the digits that are repeated on top, the 2, 7, and on the bottom, because there are 2 digits repeated, I put 2 9s on the bottom. 27 over 99. Now this one can be simplified. 27 divide 9 is 3. 99 divide 9 is 11. So 3 over 11 is the same as 0.27 recurring. Let's look at 0.102 recurring. It's the same idea. Here, the 1, the 0, and the 2, all the digits after the decimal point are repeated, so we can use the quick method. On top, we just write the digits that are repeated in order. 102 is repeated, and on the bottom, we put a string of 9s. Because there are 3 digits repeated, we put 3 9s on the bottom. So this isn't an easy one to simplify, but hopefully you can see both of these are divisible by 3. Remember, if the sum of the digits of a number is a multiple of 3, that number is divisible by 3. So 102 divided by 3 is 34. 999 divided by 3 is 333. And there we're done. All right, now I need to show you another method that we need to use when you have more than just the repeating digits after the decimal point. So this second method I call the algebraic method because we use algebra. We need to use it for decimals like these. So how do these numbers differ from the types of decimals we were looking at on the previous slide? Well, here, not all digits are repeated. So what do I mean by that? If we look at this decimal, it basically has a terminating and a recurring part. The 9 is terminating. It doesn't go on forever. Only the 3s go on forever. So this has a digit, 9, that is not repeated. It's not part of the reptend. That's when we know to use the algebraic method. So what we do is we let x be the number, so in this case 0.93 recurring. Now what I have to do is multiply this by a power of 10, so only the digits in the reptend occur after the decimal point. So that sounds a bit complicated, but can be done really easily. See, if we just multiply by 10, we move the decimal point 1 spot to the right. So x times 10 is 10x. If I multiply 0.93 recurring by 10, I get this. So now I've changed it so that only the reptend, only the digits that are repeated are after the decimal point. Now you actually need to do that twice. So what else? What could I times this by so that I get just the repeating digit after the decimal point? Well, if I times it by 10 again, 10x times 10 is 100x. I'm going to move the decimal point one spot over. See, this number is 0.933, and the 3's go on forever. So if I times this by 100, I just move the decimal point 2 spots over. It becomes 93.3 recurring. So the reason that we want both of these to have just the reptend after the decimal point is so we can subtract them. So 100x minus 10x is 90x. Now 93.3 recurring and 9.3 recurring. When you subtract them, you just get 84. See, when I subtract these digits after the decimal point, the reptend will disappear, and 93 minus 9 is 84. See, now I have an equation that I can turn into a fraction really easily. This is 90 times x. So all we need to do is divide each side by 90. We get x equals 84 over 90, and we can simplify. So 84 divided by 6 is 14. 90 divided by 6 is 15. So 0.93 recurring is 14 over 15. Let's try this one here, 0.916 recurring. So again, we let x equal that number. So now we want to multiply this by a power of 10 to expose the reptend. Well, I'm going to need to move the decimal point 2 spots to the right, which is the same as timesing by 100. So 100x will be, decimal point is now over here, it'll be 91.6 recurring. I need to multiply this again. That's so I will be able to subtract. So I'm going to multiply all of this by 10 again. So 100 times 10 is 1,000. So 1,000x will be 916.6 recurring. Again, just moving the decimal point 1 spot to the right. Now that I have the reptend and only the reptend after the decimal point, I can subtract. So 1,000x minus 100x is 900x. 916 minus 91, so just subtract 100 and add 9, you get 825. So these reptends will cancel out. That's what I wanted. That's why I did it. So dividing each side by 900, which is the opposite of timesing by 900, I get 825 over 900. So sometimes these are not easy to simplify, but here we can see clearly that both numbers are divisible by 5. So you can use short division if you need help doing the division. Turns out 825 divided by 5 is 165. 900 divided by 5 is 180. It turns out you can divide 165 by 15 and you can divide 180 by 15. It's okay if you have trouble simplifying, just keep simplifying over and over again until you get a fraction that can't be simplified. So that's that one, 11 over 12. All right, let's do this last one, 0.125 recurring. So I'm going to let x equal the number. So I'm going to times x by 10 because that will move the decimal point 1 spot to the right, and I will still have the same set of repeating digits after the decimal point. So now I need to times this again. Because there are 2 digits in the reptend, I'm going to need to move the decimal point 2 spots over. See, 10x is 1.252525. So I don't want to move it just 1 spot because then what's after the decimal point will be slightly different. I want to move it 2 spots. So here I'm actually timesing by 100. I'm going to times 10x by 100, and that gives 1,000x, and that will move the decimal point 2 spots. So now I subtract. 1,000x minus 10x is 990x, and 125 minus 1 is just 124 once again. Because I made it so that the reptend was exposed, when I subtract, gets rid of it. So x there is going to be 124 over 990. So once again, just keep simplifying until you get to a stage where you can't anymore. So I can divide top and bottom by 2. I get 62 over 495. Now I know that I can't simplify this any further because 495 is not divisible by 31, nor is it divisible by 2. They're the only proper factors of 62, so I know I'm done. Alright, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.